What is DNA? DNA is a deoxyribonucleic acid. But how is it made? So, to begin, we'll start with a song. Everybody loves DNA. So this is how I remember it. We love DNA, made of nucleotides, sugar, phosphate, anaphase, bonded down one side. Adenine and thymine make a lovely pair. Cytosine without chromium would feel rather bare. So remember, those are our bases. Once we get that, let's take a deeper look into DNA. Let's take a look at replication. Replication is DNA doubling before cell division. There are 4 very easy, simple steps to replication. Initiation, unwinding, elongation, and termination. Let's go a little closer. Initiation. But what is that? Initiation is an initiator protein that must first bind to the replication origin, and a short piece of DNA will then unwind. Unwinding. The DNA helicase comes in and breaks the remaining hydrogen bonds between the 2 nucleotide strands, which will go from 5' to 3'. A single-stranded binding protein, which is SSBS, will then attach to the single strand to prevent secondary structures from forming. DNA gyrase is another essential enzyme that will help relieve torque that's built up in the unwinding of DNA. Elongation. A primase will add an RNA primer because of the 3' OH group has to be present in order for DNA synthesis to initiate. A primer is added before every Owlsaki fragment begins. But what is an Owlsaki fragment? It's the gap between continuous and discontinuous DNA, otherwise known as your leading and your lagging strands. DNA polymerase 3 then adds new nucleotides to the growing 3' end. DNA polymerase 1, however, is also an important enzyme that removes the RNA primers and replaces them with DNA. After DNA polymerase 1 has replaced a primer, DNA ligase is then used to seal up the gaps between any new DNA strands. Step 4, termination. There are 2 ways that termination can happen. The first is 2 replication forks meet. The second is a termination sequence blocks the helicase from moving down a DNA strand. So let's take an overview. Here we'll see where the DNA unravels, your replication in this place comes in, you have your single strand, and you have all your primers that have come in to show exactly where your DNA will have your replication. But what happens after DNA replication? Follow me. We enter the world of transcription. Transcription, a promoter, RNA coding region, and a terminator. 3 lovely things. Let's take a deeper look. We have 4 steps. Initiation, where you can see your DNA is in its double helix form. You'll have transcription apparatus that will bind to your promoter region. Here is our promoter. Your RNA polymerase is then able to bind to the promoter and begin synthesizing RNA. Your RNA will continue from your 3' end of the RNA molecule, and it's complementary and anti-parallel, which is very important because it's complementary and anti-parallel to your DNA strand. Next step, elongation. As you see here, we have it labeled your 3' to your 5'. What happens in elongation? As you can see, here has widened. Your RNA polymers will continue to unwind your DNA as nucleotides join into a growing RNA strand. And here's where the difference is between your initiation and your elongation, is your RNA strand has been attached to your RNA polymers. Our last step is termination. Once your RNA polymers transcribes, the terminator transcription stops. So here we'll have our stop sequence. Your RNA polymers will detach from the DNA template, and your RNA detaches from your RNA polymers. As you can see, this is now detached from our double helix strand, and our RNA has also detached from our DNA and our RNA polymers. So that's a close look into transcription. But before, we need to remember that there's one last step, and it's probably the coolest and my favorite. So come on. Translation. Translation is probably one of the easiest ones to remember for me. You have your tRNA charging. What does that mean though? It means that your tRNA will bind to a specific amino on your 3' end. Recognition of this apparatus though is your AA, and it will be based on its size, its charge, and its R group. Let's break that down a little bit more. Just like our transcription and our replication, we have initiation in this one. Right here, you can see we have our A site, our P site, and our E site. But what does that mean? So, our mRNA will bind to a small subunit, which is going to be right here, of ribosome, after which your initiator, tRNA, will bind to the mRNA base pair, pairing between the codon and the anticodon. The large subunit of a ribosome then forms an initiation complex, after which we have elongation, which elongation can be broken into two different ones. It's elongation and then translocation. So, elongation, there are 3 sides of the tRNA that can occupy. You have your E site, which is your exit, your P site, which is your peptide bond, and you have your A site, which is your amino acyl sites. Your P site's your peptidal, sorry, not a bond. So, in elongation, the initiator, tRNA, starts to occupy the P site, which is the same over here. However, another tRNA will come in and bind to your A site, after which your amino acids on each tRNA form a peptide bond, which allows the amino acids to be released from the tRNA in the P site. After that, we go to our last step of elongation, which is your translocation. Translocation is where the ribosome will move down to the next codon. So what that means is your tRNA in the existing P and A site will then shift down, and it will move to your P and E site, leaving your A site completely occupied for another tRNA to come on in. But what happens mainly in this is that it forms a growing chain. As you can see, our S is bonded to our M, so it forms a peptide bond, which will increase a growing peptide chain. Our last step, termination. As you can see, this is floating, but elongation will continue until a termination code is translated. After that code is translated, a release factor binds to the A site, which we'll remember is the one closest to us in the ribosome. The release factor causes the tRNA and the mRNA, however, to be released to form a ribosome. As you can see, this is completely released from any of our E, our P, or our A sites, and it's on its own, forming a longer chain. But that's the end, right? The most important thing, though, to remember with DNA is it has to replicate, it has to transcribe, and it has to translate in order for anything to happen. And without it, we probably wouldn't be here. Thank you again for watching this amazing presentation, and I hope that it's good enough to get me the bonus points from Dr. Mukhtar's class in Biology 210, spring semester of 2016.